So let me continue now and say something about recent simulations that we did in the context of X-ray binary jets. Reason being, because at the very beginning I already drew the parallel between AGN jet and X-ray binary jet, and I actually drew the parallel with the observations from this well-targeted system SS433. And that is exactly the simulations that Remy has been doing since. And so I'm happy to share this with you that is now, in fact, accepted for publication. Because recalling that now we're interested in the dynamics of a precessing jet, okay? This jet that was actually associated with the accretion disk around a few solar mass central black hole, being fed by a Roche lobe overflowing companion. We're actually going to go to scales that match on these VLA type simulations. And so we're actually going to, again, we cut out a spherical region of the order of 0.008 parsec or so. So again, the system itself and the launch processes are not dealt with. But we know that there is a jet that has a certain opening angle, which is known. In fact, we take values from the literature, and we include we take it a little bit wider than the actual value known for this opening angle, because the point is that this jet is not only precessing around this axis with a period of about 165 days or so, but it's also nutating on its orbit around. So the nutation, in effect, is incorporated here as a sort of a slightly wider opening angle of a few degrees that we take on this thing. And then this is basically the way in which we inject the jet. So there is this spherical inner boundary, and then we have these precessing beams, both ways, that, inject jets. And again, the main reason in which this jet enters is we take the parameters from the observations and we vary them within meaningful bounds. So here is a snapshot. So we take 3D hydro, but relativistic hydro runs. And here I'm showing you a snapshot of a simulation that I'm going to show. What is actually, again, there is this central region. And now we go here on the order of 0.2 parsec or so. And you can see here the end state in which the jet has basically formed a helical pattern. And you can see here how on this helical pattern we have, we have quantified the pressure. So one of the things you can note is that the high pressure zones are, of course, so where there is interaction with the interstellar, with the surrounding medium. So they are located, obviously, on the front side of these helical patterns. You have then rarefaction zones at the back of the jet. You actually have in the cross-section the density pattern quantified. And so we take the jet speed as determined by the observation. So this is 0.26 or so speed of light. And then suppose we have an over-dense jet, so denser than its surroundings. Then the simulation basically will look like this. So you have here how over this period you see now the jet being injected, and there are many precession periods actually being followed over this time. But it takes a while to build up the I'm going to try and play this again. You should note that it takes a while to build up full helical patterns up to a certain distance away from the source, because obviously you first have to, sort of influence the surrounding medium. And you can see as further that we progress, we can actually get a nice helical pattern out to the distances that we were able to follow with these simulations. And if you look at the thing in a cross-section, okay, then you see that actually this jet is behaving like this is density. And so actually these individual blobs, okay, they are basically launched on radial patterns. Okay, they are just, you know, because they are shot out with a certain relativistic velocity, fraction of the speed of light. So they just happily move on a radial. They interact with the medium. And the appearance of the overall helix is more the fact that, you know, we are continuously shooting these individual blobs, but in different directions, rather than something that is shooting out straight and then deforming. Okay, so that's sort of an interesting observation. And we have been able to then produce radio maps. I'll show you, and how they match with observed VLA maps. So this submitted has been happening, and it has been accepted now. So here is, in fact, a contrast between, let's see, on the left is a picture taken from this paper by Roberts et al., 2008, where they have VLA observations. And so here these are contours at, for the radio. Of course, there is also now a centrally peaked thing, which corresponds to the fact that, okay, the central regions obviously form a strong radio source. And then overplotted here is what is known as this canonical model, this kinematic model for SS433, which is nothing but if you have a precession of 165 days and you shoot continuously with 0.26c, then this is the pattern that you should see. Okay, that's nothing but kinematics. And the main point that you should note from this observational thing is that this kinematic model is systematically sort of overestimating the distances to actually observed features. Here we have a virtual map where now you notice that our virtual map also has a central source, and I said that we don't have a central source. We actually added a central source by hand because we didn't simulate that, okay? But we followed as a recipe to turn our hydrodynamic, our relativistic hydrodynamic simulations into radio observations. We actually simulate more than the relativistic hydro equations. We actually also simulate evolution equations for quantifying a relativistic particle populations with a given slope in its energy spectrum. But with the cutoff energy being determined by these additional simulations, and with this whole, well, we inject these particles along with the jet at the bottom, and they are influenced by adiabatic compression and refraction things. So that's an additional set of equations that we solve along, and then we can ray trace through it. Now, still we need to do something because we don't have a magnetic field, and this is, of course, based on emissivity that scales with magnetic field components. But there we do the cheap thing, where we take equipartition, so pressure related to magnetic field squared, and thereby we can turn our things into radio maps. And that turns out to be fairly successful in reproducing features that are, well, with a little bit of arguing, are seen in the actual observation maps. And also here we have this delay between, if we were to overplot a kinematic model, I haven't shown it on this plot, but we have it in the paper, we have this systematic, difference between the kinematic model and the positions where you see individual features. But now we can explain why, because, well, as I showed you, it takes a while to build up a helical pattern because of, well, first the jet must actually interact with the medium, and thereby the whole history of the jet formation process influences the position where you ultimately get a kind of a helical overall pattern. And you can do with what we have done is vary the precession angle for the jet. I mean, for SS433, we know very well that this precession, the angle between the rotation axis and the jet axis is 20 degrees. So there's little reason to change it, except that the same jets from SS433, they happen to also interact further out with a supernova remnant, and their recent work has actually showed that on the basis of numerical simulations, hydrodynamical simulations, the kind of morphological patterns that you see as this jet interacts with this further out supernova remnant pattern is more in line with a 10-degree opening angle, okay? So that's why we also did a 10-degree opening angle jet, and then indeed, obviously, we get a narrower, spiral pattern. And the map, the radio map from this case, doesn't really match with the actual observations. So if there ever was a reason to invoke 10 degrees, it has to be an evolutionary argument or something that happens on the way through these. This is 0.1 parsecs, and the people then talk about 10 parsecs or so. Here we vary the speed, okay? Here we vary. The speed is well diagnosed for SS433 to be 0.226c, okay? Here we went to higher relativistic speeds, so 0.845 speed of light. You see a pronounced difference in this pattern, and the reason is that by changing the speed over this, what seems to be a modest factor, we're actually changing the fact that we go from overdense to underdense jet conditions. And that means that in this latter case, underdense, it first has to inflate a bubble, okay, and, deposit a lot of energy in this inflated bubble before it can start to make a more coherent, overall spiral pattern. Other things that we can do is, if we vary the speed, then in the cross-sectional view, here I'm not showing the density as I showed in this movie, but the sound speed, you can see these blobs and how they interact with the medium. So this is the canonical overdense situation to underdense situation, and you can see there sort of the large-scale bubble inflated and the effective slowdown. So these are the things that you can then use to quantify the overall propagation characteristics when we vary these parameters, which, of course, we cannot vary in SS433, but we can vary in our simulations. So far, I managed to get one of my lectures done. And I showed you that, the simulations that I've shown so far, especially those that I showed at the letter, are all gas dynamics, okay? I showed a few exceptions of magnetohydrodynamic simulation, but those were non-relativistic, okay? And so I think there's still a lot of room for going beyond this, and I will try to show a little bit on that in the next part. And scale encompassing studies for this feedback aspect, on the one hand, they're impossible, but on the other hand, the whole process of how jets are launched from accretion disks and how they then influence and deposit their energy in the far field is parameterized in this whole feedback scenario. So we better improve this situation somehow. All right. I still have half an hour today. So, no, this is not what I wanted. No. Depending on time, I'm planning to tell you a little bit more about the equations that I've actually been solving. These relativistic hydrodynamic equations. And because it's about cosmic magnetic fields, I need to tell you about relativistic magnetohydrodynamic equations. Because I guess one of the first things that you heard about MHD is that the first thing we do is take Maxwell's equation and drop what Maxwell added, right? The displacement current. So we went back to pre-Maxwell and then could live with everything that doesn't flow with the close to the speed of light. You can, without any problem, also formulate MHD in special and even general relativity. And I'm going to show you how that works. And then, we'll see how far we get. One of the things that I cannot stop but advertising is, if you're really interested in MHD, this book, 2004, written by Hans Goedbloed and Stefan Putz, is a very nice overview of magnetohydrodynamics, Newtonian MHD. And I have had the honor and privilege to contribute to the follow-up book, which has been published with Cambridge in 2010, on advanced MHD. And some of the stuff that I may or may not share with you is written in that book. So you can leave and go to the library and read the book if you want. But the part that I was planning to say a little bit now is the closing chapter in this book. How relativistic MHD is formulated. So we go to Relativity 101. And let's deal with special relativity. It's already complicated enough because we have a 4D, but in special a flat space-time, okay? And that means that we have to start living with 4 dimensions. And the 4th dimension, next to the 3 spatial dimensions, is time. Time multiplied by the speed of light gives another length. And so that is a 4 vector. And from this 4 vector, this combination of these 4 coordinates is an invariant, the squared length invariant, where the only thing that you are undoubtedly familiar with is that, well, time is a different sign than these others. That's the Minkowski metric, so minus 1, 1, 1. And because it's flat space-time, it's still simple in terms of relativistic because, you know, normally you have to live with differences between covariant and contravariant components that are then quantified by these metric elements. But in flat space-time, the difference between that is just, you know, whether or not you have, well, a minus sign in front of the first derivative. Anyway, what is a familiar concept? So we now have 4-dimensional space-time, but I cannot draw 4 dimensions, so I draw 1 space dimension and 1 time dimension. And then, of course, the speed of light sets a limit to where things I can actually go through. And this is sort of indicative for a world line of a particle, okay, that traverses 4-dimensional space-time, this solid line. And what I'm saying is we're actually introducing a 4 vector that connects my coordinate, my origin of my coordinates with the instantaneous position on this particle world line. That's my 4 vector, right? And what I'm going to quantify is also the tangent vector in this 4-dimensional space to this particle world line, okay? And that is going to be my 4 velocity, right? That's 4 velocity, and that is the derivative of this 4 vector with respect to the time that I and I alone am happy with. Namely, I have my ideal clock traveling with me, and that sets my time change, okay? My proper time tau. So, to compute the 4 vector to the world line, what I'm going to do is actually translate everything to this familiar split in time plus space, because that's the one I knew best from Newtonian MHD, and I'm assuming that's the same for you guys. So I'm taking this 4 velocity, and I just have to take the derivative with respect to my clock, my proper time. And so then I need to just derive this with respect to tau. And that means that this temporal component is going to quantify a familiar concept, that time is dilated, right? So you have the fact that we have time dilatation. And that is actually quantified by the Lorentz factor, okay? And then the spatial part is, well, I'm going to first take the derivative with respect to the time in my Lorentzian reference frame, because that's kind of convenient. That's what I always called my velocity, my 3 velocity. And then I have to take, again, time dilation into account. So actually, 4 velocity is just c times Lorentz factor, temporal part, and Lorentz factor times 3 velocity. And 3 velocity is what you're always working with in Newtonian every day anyway. And the Lorentz factor you know. Okay? And you know that if I have my proper time and then you have your proper time, we're not going to agree anymore on things that are simultaneous. And when we move in relative motion, the only things that relate your perception with mine is Lorentz transformations, okay? And this Lorentz transformation, which just involves the relative speed, right? And says how my time and my spatial coordinates differ from your time and your spatial coordinates, is expressing mathematically loss of simultaneity, length contraction, time dilatation. So if I start with particle density, particle number density, okay, then I can reason as follows. So you have here proper density would be sort of, rest mass times a rest frame number density. Okay, I'm going to quantify number densities in the rest frame. And then I will differ from a lab density by the fact that, well, if things move past with a certain speed, then the volume will be influenced in the direction of the motion, and so there is length contraction. So it shouldn't surprise you that there is a factor of gamma, Lorentz factor, in between. And particle conservation can just be expressed, well, in sort of the most proper notation, of course, for relativity is just taking the derivative with respect to all the components, so the divergence of this 4 vector equal to 0. But if I insist on writing this in a time plus space thing, then I get, for this lab density, it's actually not really the density because there's also a Lorentz factor part in this mass thing, but okay. Then this is the, well, conservation of mass, but now relativistically fine, okay? And now it looks like the non-relativistic version, of course, with the only difference that there is a Lorentz factor gamma. And of course, if gamma goes to 1, then this is mass conservation. Okay, so that's particle conservation, particle normal conservation. Okay, but now I cannot longer speak separately from momentum and energy. I have to combine that in a 4-dimensional stress energy, okay? So now the stress energy tensor, okay, has then, I'm always going to try and split things that are happening in space with things that involve the temporal dimension, all right? So in the fully temporal part of the stress energy tensor, that should be an energy density, okay? In those off-diagonal components, that should be, respectively, energy and momentum flux. And in the spatial part, these things are stresses, okay? So if we take this, then I can write down what the stress energy tensor is almost instantly if I'm in the rest frame of the matter. Because in the rest frame, there are no energy fluxes and no momentum fluxes. And if I have an isotropic pressure, then that diagonal pressure, 3 by 3 vector, is setting my isotropic pressure. And my energy density, I know, I mean, it is my internal energy that I was always used to work with already in Newtonian cases, right? So this is sort of the P over gamma minus 1 plus the rest mass. Okay, so now I have this thing, which is the full expression for, if I just have a gas, okay, for stress energy tensor in the rest frame. But I don't need it in the rest frame, I need it in the lab frame. But that's easy to change because I can just inverse Lorentz transform. And I know the Lorentz transformation, or I can look it up in a book. It's something that takes this into this expression, where I now have introduced these energy momentum fluxes, and then these, well, energy densities and stresses. And, okay, this is just simple mathematics, I guess. This is, of course, just when you have a gas. So when you have a plasma, you should also, of course, consider electromagnetic fields. Now, for electromagnetic fields, I think it shouldn't come as a surprise that the electromagnetic stress energy can be quantified similarly, again, because in this part, temporal, I just need an energy density. I know the electromagnetic energy density for an electromagnetic field because it's B squared over 2 mu plus epsilon E squared over 2. This is a vacuum type expression for magnetic and electric field energies. I also know energy fluxes. I mean, that's the Poynting flux, E cross B over mu. So I have the off-diagonal expressions. And I am familiar with the Maxwell stress tensor. Maxwell stress tensor is just, well, this expression for electric and magnetic field 3 vectors, which are specific to my Lorentz frame, my lab Lorentz frame that I have chosen, and in which I'm also talking about 3 velocities, etc. And now this involves electric and magnetic field. Ideal MHD works just like in the Newtonian case. In the co-moving frame, I short-circuit everything. I have perfect conductivity, meaning that electric field 3 vectors are directly related to velocity 3 vectors and magnetic field 3 vectors. And that allows to transform this into some equations. I add now this part electromagnetic with this part for the gas/plasma, and I take the divergence of that tensor, and then I write down what my temporal part and what my spatial part gives. And then I have equations that look like what I had before, and the partial derivative of respect to time of a quantity plus the divergence of something is equal to 0, and the partial derivative of a momentum vector to some total momentum vector plus the divergence of something equals to 0. Okay? In here I have now already used this ideal MHD trick to get rid of the electric field appearance in there. But I haven't neglected the displacement current. I am now fully consistent with the full set of Maxwell equations. But because I have no need for the electric field, in a sense, because I can still live with closing by homogeneous Maxwell equations. And that means that I have the same induction equation as Phil and Fausto already discussed to you at length, so I don't need to do that anymore. Good. And of course, divergence B is 0 or an elephant, depending on the T-shirt. And then you have to close this with an equation of state. You could take this kind of relations. This is the sort of relation that in Newtonian gas dynamics you would use for internal energy with a specific polytropic index. But as I said before, in fact, you can, well, also account for the fact that you may reach things that in terms of, well, a temperature is always related to internal, fluctuations, right? If those internal fluctuations also happen to become close to relativity, things change. And that is in effect translated to this polytropic index changing from 5/3, which is the classical monoatomic ideal gas kind of value, to 4/3, which in turn change possibilities for compression ratios, etc. And that changes with temperature. Here I show two lines that are representing what is known as a singed gas and an approximation that is more convenient. I don't have really the time to go into this, but these are things that you can easily take along into your simulations, and that is what has been done. So special relativistic magnetofluids in flat Minkowski spacetime actually boils down to ideal MHD approximations and a set of conservation laws that in a time space split look like something that you can plug into your favorite numerical code for solving hyperbolic differential equations, partial differential equations / conservation laws. The tricky thing is here that, okay, my conserved variables have somehow changed except for the magnetic field. And these fluxes, okay, these fluxes, I have expressed them here, V cross B, and then here these expressions. So the point is that whereas in Newtonian MHD, the difference between what is known as conservative versus primitive variable is almost trivial in the sense that, well, yeah, it's just an algebraic relation, right, between them. Total energy density is made up of internal energy density plus kinetic energy plus magnetic energy, but that's an algebraic relation. Now, there are these Lorentz factors all over the place, and Lorentz factors have these square roots, and so it's no longer algebraic, and you have to do actual numerical root-finding procedures to switch between conservative and primitive. But, okay, at least nowadays we can do root-finding fairly accurately. So the Newtonian limit, I mean, you know the Newtonian limit, this is the limit when you go for Lorentz factor going to 1. You go to conservation laws for density, and this is what mass conservation was. The only thing that has changed is that we had the new quantity is this rest mass density times the local Lorentz factor. Okay? That's simple. This is the momentum density equation. Again, what happens there is that where this total momentum, well, I have a few slides here, okay. This total momentum is this, and then, okay, you have to collect a few terms that have appeared on the slides. I'm going to tell you that with these introduced variables, we actually land in the Newtonian limit on this, which you may or may not recognize as the momentum equation written in conservation law form, okay, where the contribution of the Lorentz force is split into its tensional part and pressure part over these two parts here. Energy density, well, this tau quantity goes to the familiar internal plus kinetic plus magnetic. This is what I was saying a while ago. And so in these chosen variables, the Newtonian limit is sort of, well, what you get when you set gamma goes to 1, which is basically what you expect, right? And there is nothing to be done here. This is the same equation that you had, the induction equation, in a form that I'm sure also has passed the review. This is the same. And now, I contrasted, I gave you in a nutshell just the governing equations of special relativistic magnetohydrodynamics and how they relate to the Newtonian, okay? one thing that I think you also were told is how to get to the wave speeds in MHD. Okay? I think I saw that on your slide. You never got to it. Oh! Yes. Okay, I have to get to this. And then we close. Okay, I promise. So what you do is you take these equations, which you have shown and which I have shown, and you have a background steady solution. And the simplest background steady solution you can imagine is you have a uniform pressure, uniform temperature, and uniform unidirectional magnetic field. And who here in this room is familiar with the Friedrichs diagrams and the group diagrams for the waves? Except you. Really? Okay. Gas dynamics. Who is familiar with the phase speed diagrams and the group speed diagrams for the sound waves? Yes. What do they look like? What do you expect if I do this? What happens? Physically. Yes, sound waves. And what is particular about sound waves? Compressions of density, and they have a speed. I would call it a sound speed. And if I do this and you sit there or you sit there, will it make a difference? Okay. So that's the most important point. I will draw the diagrams for gas dynamics. So here is my point. And I can draw a circle. Voila. This circle quantifies two things. It quantifies both the phase speeds and the sound speed and the group speed. Who knows the difference between phase speed and group speed? It's late. Yes. Yes. Right. And the group speed is del omega del k. Right? Physically, what I'm looking at is I'm actually going to work with plane waves. Okay? And plane waves, they just treat the problem in Fourier space. Okay? And so we have a frequency with time and a wave number, wave vector, actually. That wave vector quantifies two things. I'm interested in plane waves. So plane waves just really are plane, infinite. And you separate troughs and peaks. Ultimately, subsequent troughs are separated by one wavelength, right? That wavelength relates to the wave number, k, by, 2 pi over lambda is k, all right? So they relate to each other. And the direction of k gives the direction in which these plane waves propagate. This diagram here tells me that if I launch a plane wave in this direction, it will travel this distance in a fixed time. And so my plane wavefront will be here if I launch it in this direction. If I launch it in this direction, it's gas dynamics, so it's the same. My plane wavefront will be here after the same time. And so that's how I come to a circle. But if I take now the following, okay, in that sense, this diagram tells me for all directions in which I can launch a wave, I end up at the same distance, and hence I get a circle for the phase speed. Now, the group speed is related to energy transfer and to, well, wave packages, okay? So that is what I actually did when I knocked my hand. I'm launching basically, well, yeah, sort of plane waves in all directions. So actually, this group speed in some sense tells me, okay, where does the energy end up if I do a localized perturbation, all right? And there are two ways to do this. Mathematically, what your friend said. Graphically, you're interested in launching plane waves and seeing where they constructively interfere, okay? So you can go back to optics, where you are maybe familiar with the Huygens diagram, okay? And the Huygens construction, sorry. And so you need to basically see if I have these plane waves all over this circle, where do they constructively interfere? On the circle, so I have the same between group speed and phase speed. In MHD, I have a physical direction. I have the direction of, even in a uniform plasma, I have a direction of the magnetic field. And that means that if I do this thing that, well, you know, Fausto should have done, you take the MHD equations, you linearize them about a uniform state, you assume these spatio-temporal dependencies, and then you look for solutions, because you don't have boundaries. It's a uniform plasma up to infinity. Then you get a relation between omega and k that has, well, how many should I have, actually? How many equations do I have in MHD? Eight. How many equations, how many waves do we expect? 3. There's a big discrepancy here between 8 and 3. So it should be somewhere in the middle, right? Let's count the equations. Conservation of mass is 1, right? We all agree. Conservation of momentum is 3. So we have 4. We cannot live. And then energy is 1. So in gas dynamics, how many speeds will I have? Five. I will have 5 speeds, right? I will have 5 speeds. 2 of them will be sound. Why 2? Because there's one going this way and one going that way. And 3 others will be just the in-place velocity. They are respectively related to entropy disturbances that allow me to set up a constant density discontinuity without anything else, and shear waves. So there are 5 waves in gas dynamics. I only have 5 minutes. Okay, now go back to MHD. So we were at 5. We still have the induction equation. So that is this 8. Okay, I have this thing. So I have these 8. But then I have a constraint, right? I have div B equals 0. That's not a temporal thing, so I subtract it. So I have 7 waves, all right? Message is MHD, as a hyperbolic system, has 7 wave speeds, all right? So which are they? You said, somebody said 3. Yeah? What are the 3 that you were expecting? Somebody? Right. 6 of these 7 are the fast, slow, and alphane in both a forward and a backward variety. And then there is the 7th. This is the entropy wave. The entropy wave is the most boring thing you can ever imagine in ideal MHD. But add non-ideal effects, and it's become very interesting, because then it's thermal instability and whatever, you know it. So anyway, if you just do ideal MHD, then you can get this relation, and then you can plot it if you want. Suppose that you fix a certain wave number, and a wave vector, sorry, that has to have 3 components, right? So kx, ky, kz, and the z direction is the magnetic field direction, so that is the parallel. And then I can plot this thing where I keep ky and kz fixed, and then I can plot it as a function of kx. And then this dispersion relation, which, well, Fausto should have told you, is this thing here, all right? This is the fast branch, the Alfvén branch, and the slow branch. I have now introduced kx, a wave number in the x direction, which is one of the directions perpendicular to my magnetic field. So let's consider a magnetic field trapped between two plates, and let's not go to infinite space, but to bound space. Then what I get is that I will not be able to have all wavelengths in the x direction because it's bound, so I have to fit with either 1, 2, 3, 4, 5 oscillations within this thing. And that means that I get from continuous curves to just the dots at integer wave numbers that fit in the box. And if I then project these curves onto the omega squared axis, all right, I will get fast waves. Those familiar with helioseismology, they should say, aha, this is the pressure, P modes. Then we have the Alfvén, and then we have the slow, all right? So here, this is a schematic diagram, okay? And if I ever get to it, I will tell you how it changes with background flow. Now, the phase diagram, I'm going to skip to here. These are the diagrams that are the equivalent of the phase and the group speeds for MHD. And I guess that's probably going to be the end of it. This is the phase diagram. Again, what tells this diagram? This tells me for all the directions, the magnetic field is horizontal and uniform. For all the directions with a certain angle with respect to this field, if I launch a plane wave, how far will it travel? And this depending on whether it's in the slow, the Alfvén, or the fast wave category. And then I will see that I cannot launch Alfvén waves perpendicular to the field. I cannot launch slow waves perpendicular to the field. And my fast waves, they don't travel isotropically either, because in the direction perpendicular to the field, they are aided by basically the Lorentz force, which is perpendicular to the field, right? And so they travel faster in that direction. This is the phase speed diagram. If I take this diagram and I do my Huygens constructions, I will get this diagram. This is the group diagram. And the point is that these Alfvén guys actually turn out to be circles, okay? With in the direction parallel to the field, it's given by the Alfvén speed, and then this is just a circle, all right? And this is a backward and a forward one. And as an exercise for tonight, if you take two circles and you make a Huygens construction, what do you get? You basically get 2 points in which these constructively interfere, and those are the Alfvén waves. They only travel along the perturbed magnetic field line. All right? So this thing here is the group diagram, and those dots are the Alfvén waves. So I have now, on the right, I actually have an experiment that I will show you later, hopefully at some point, in numerics, which you can do at home with your favorite code. You just do a point perturbation and see what happens in MHD. Or in gas dynamics, you know what happened. In MHD, you now also know what happens. These Alfvén waves will travel along the perturbed field line and only along the perturbed field line, nowhere else. This one singular field line that is perturbed. The fast waves behave almost like sound, but not quite because they are anisotropic. And then these slow waves constructively interfere to form these triangular patterns. This, maybe I can show this. I don't know whether I have it. Oh, yeah. This is what you should get in a particular case where, oops, I tried it again. All right. So if you point, then here, these are my Alfvén waves. These are my cusp, my slow waves and my fast waves. And there are 7 waves in the MHD case. I show you here 6 because the 7th is also here. It's that dot here. Okay. But I don't show it in this movie because the movie is showing me the pressure, and in pressure it's not seen. So you have to look at either density or entropy, and then the point that you perturbed, depending on the perturbation that you put, may leave a point perturbation that is the entropy perturbation. And then you see all the 7 waves. And that is non-relativistic, Newtonian MHD. And maybe tomorrow, tomorrow, I will pick up on this and then tell how this thing changes in the relativistic MHD.